Perfect.
I just hit record just in case.
Perfect. Yeah. So please know that all video conference sessions are recorded and archived. During these sessions, the typical expectations of our classroom and our school apply, albeit you can have your dog. This tool is only to be used while the teacher is present. No part of the session is to be recorded or redistributed by any student. All right, then. So I just wanted to kind of touch back to last week, and actually Mr. Chisnell sort of started that by showing some of the books that he referenced in our last session. Last time we talked about some of the limits of scientific knowledge and methodology, and today I want to think about why we should believe in science and what other people have to say about science and the questions that come from science or within science. So before we even get started, I'm going to share my screen and I'm going to ask Mr. Chisnell to count for me. He's going to keep track of something for me. He's got a job and it's an important one. All right. So what I'm going to do when I show my screen, I'm going to show you ToK's ways of knowing. And I want you to think for a moment about, can you see my screen, everyone?
Yes.
Perfect. I want you to think for a moment about which two of these ways of knowing do you think science relies upon? So which two are most important? And we're going to just take a very informal poll. And how I'm going to do it is I will name each one, and each of you, and we're going to trust that you're only voting twice, just raise your hand. Mr. Chisnell will take a little tally, and we'll just sort of put that away and see if we change our minds at all by the end of the class period. Does that sound good?
Does my vote count?
Yeah, you will count. I will name it. People will raise their hands. You'll do a tally for each one. Does that sound fair?
Sure.
Okay. All right. So again, each of you only gets 2 votes. So how many of you think that language is in the top 2 ways of knowing for natural science? Raise your hand.
Just me, it looks like.
What's that?
Just me.
Just you. Okay. How about number 2, sense perception? Is that in the 2 top most important ways of knowing? Raise your hand.
0.
How about emotion?
0.
Reason?
We got a bunch there. 4 there.
Okay. Imagination?
Gotcha. 2 there.
Faith?
2 there.
Intuition?
And intuition. 1 there.
And memory?
And 1 there. Interesting.
Okay, so this is sort of just a little experiment. I just am interested to see where we are and if we change our thinking on that at all. Okay, so the next thing I want to do is I asked my students to listen to the TED Radio Hour, recognizing that maybe not everybody did or may have had some problems. I thought we would listen to a segment of it together. Just take some notes, and then we will discuss. Does that sound good?
Yep.
Thank you. Thank you for speaking back to me, Mr. Chisnell, since I can't see your faces.
I'm voicing their thumbs ups.
Thank you.
Question is often more important answer. Focus. Thank you very much.
Hold on. So my daughter is trying to send me notes. Dad is running, I think. Thank you very much.
That is
Naomi Oreskes. I'm the professor of the history of science and affiliated professor of earth and planetary sciences at Harvard University.
So it's fair to say that you study pretty big questions, I guess.
Right. The history of science is the history of the development of knowledge about the natural world. I study scientists. I study the processes by which they collect evidence, by which
means Naomi gets to ask the meta questions about how we know what we know.
Say science is evidence-based, but what's evidence? How do we judge whether some evidence is good or bad?
And lately, Naomi's been trying to answer one very big question, which is, why should we trust in science at all?
Scientists tell us that the world is warming. Scientists tell us that vaccines are safe. But how do we know if they're right? Why should we believe the science?
Here's Naomi Oreskes on the TED stage.
The fact is, many of us actually don't believe the science. Public opinion polls consistently show that significant proportion of the American people don't believe the climate is warming due to human activities, don't think that there's evolution by natural selection, and aren't persuaded by the safety of vaccines. So why should we believe the science? Well, scientists don't like talking about science as a matter of belief. In fact, they would contract science with faith, and they would say belief is the domain of faith. Now, the fact is, though, for most of us, most scientific claims are a leap of faith. We can't really judge scientific claims for ourselves in most cases. And indeed, this is actually true for most scientists as well, outside of their own specialties. So if you think about it, a geologist can't tell you whether a vaccine is safe. Most chemists are not experts in evolutionary theory. A physicist cannot tell you whether or not tobacco causes cancer. So if even scientists themselves have to make a leap of faith outside their own fields, then why do they accept the claims of other scientists? And should we believe those claims? So what I'd like to argue is, yes, we should, but not for the reason that most of us think. Most of us were taught in school that the reason we should believe in science is because of the scientific method. We were taught that scientists follow a method and that this method guarantees the truth of their claims.
So the scientific method, right? You have a hypothesis, you do some experiments, you make some observations, and
if the observations work or the experiment works, you say your hypothesis is confirmed and you go on and do the next thing.
But, Naomi says, the scientific method is just a starting point.
The scientist can't just say, okay, I confirm my hypothesis, now I go do the next thing. That by itself is not sufficient.
So if that's not sufficient, what is? How do scientists decide what's right and wrong?
Consensus.
Consensus.
And this is really, I think, the most important part of science that many people don't understand and that isn't in the high school textbook.
Consensus is the key. And building consensus takes a long time. Somebody comes up with a scientific conclusion. Those conclusions are then vetted by other scientists. If they check out, they're published. And then even more scientists review those results and ask their own questions.
If it turns out that when they try to use my data or my idea and it doesn't work, then they will publish a paper saying, well, hold on a second. So my claim could end up being discredited. Sometimes critics of science will point to papers in the journal that were subsequently disproven and say, oh, see, look, you can't trust science because that paper, that got published, but then we realized that was nonsense. Well, that's not evidence of what's wrong with science. That's actually evidence of what's right with science, because the claim got disproved, and then we know, okay, Naomi's an honest person. It was a good idea. We tried it, but it didn't work, so we now reject it and we move on.
So how do you know when you've reached consensus?
So imagine now I've published my paper. My colleagues have picked up on my idea and my data, and they've used and they've worked with it, and they say, yes, our data are consistent with this. And now other people do the same. And eventually we all conclude that my claim was right. And that's what scientific knowledge is. It's that moment when we all say, yeah, this appears to be right. And then we stop discussing it. The whole reason why science can progress is because there are points at which we all agree the data is secure, the data is sufficient, it's settled, we have a consensus, and we move on to the next question.
In just a moment, when we come back, Naomi Oreskes on why scientists revisit old questions, even ones you thought were settled. Today on the show, ideas about the spirit of inquiry. I'm Guy Raz, and you're listening to the TED Radio Hour from NPR.
Okay, so It's a longer piece, but I'm thinking of cutting it there. We may return to it depending on how the next part goes. But I want you guys to jot. I'm going to put a prompt up, and I want you to jot in your notebooks. Maybe you've already done this part, but I'm going to give you a couple minutes to think about the following question. Oop. Okay, so what do you think? Tyler, can you share what you wrote or what you're thinking about with her discussion about what real science depends upon?
So basically what she kept saying was that scientific consensus is, after reviews and studies and multiple tests of multiple scientists, multiple fields, going back and looking at the study that they did. And so the consensus that she's talking about is like within the realm of the scientific community. So that's excluding the outlier people that will make the claim that the hypothesis or the theory is wrong. Yeah.
Okay. Who can add on to what Tyler said? Thank you. What do you think, Anna? Anything that he missed or that you want to add on to?
I mean, I said that once we have like a consensus on something, it becomes less of like a personal opinion and more of like, I don't know, like closer to a fact.
Uh-huh. But is there ever something that just we come to the end of the line?
No.
Do we answer it all? So what happens when we might get settled on something? Is the goal of the natural sciences to solve it all, or what's the goal?
I am not sure.
I can't see your face. It's okay. I mean, just anybody. What do you think about that idea?
Well, later on in the TED Talk, one of the other speakers talked about how the scientist's goal is to find the truth, but they're knowledgeable to the fact that they don't actually know when they have reached the truth. And so they are constantly coming up with new ideas to explore, and they may think that they have an answer to to the knowledge that we have now, but that doesn't mean that in the future we will find something else that builds on to the theory that we have, or it changes our perspective of an idea, but it doesn't make the idea wrong.
And how does that rest with you? Does that feel frustrating to you, or does that feel okay? One question is going to lead to something else, and we might have consensus for a while, but like, how does that make you feel?
Well, in the realm of science, I am not entirely a science person. I am a very logical, analytical thinker. I like it when I know an answer to something. And so when it comes to science and having these big ideas, um, that's where I get lost in science because that's just not how my brain functions. I like the 2 + 2 = 4, this times that equals that kind of thinking.
Thank you. What about back to this idea of faith? Some of you thought faith was one of the major ways of knowing in terms of natural science. One of you who selected that one, could you elaborate a little bit more about the role of faith in understanding natural sciences or pursuing natural sciences?
That's me again. So I chose faith because of how much it was talked about in the TED Talk or in the podcast. And so my reasoning is basically what we just heard was with when scientists think of new ideas and they study their ideas, um, you have to have faith that what they're studying in their motivation for what they're studying is in the correct, or they have a good motivation for what they're studying. And so we have to have that kind of faith within the scientific community to trust those claims or to be able to test those claims to get a better or correct answer.
Okay. Someone else? I think I thought that there was more than one person who said faith was a major way of knowing.
Yes, there were. There's a second person. I can't remember who it was. It was, I think, Victoria or Anna. I can't remember which one.
Reveal yourself.
I said reason and memory, so.
Okay.
Okay, Victoria, what do you think about faith?
So for me, I said faith because in science you kind of have to believe in what you're doing, and the other people around you believe in what you're doing. Depending on your field, it's different for everyone, but you're not going to do something you don't think is going to work or you don't believe in. That was kind of my reasoning.
Does anyone else want to add to the just thinking about what Professor, what is her name, Oreskes, what she had to say, or anything else that you may have heard from the podcast about inquiry and its role in the sciences? Okay, it's very weird talking to a screen where I can't see your faces, so forgive me. So you all know who Watson and Crick is, yes? Are they nodding, Mr. Chisnell? Uh-oh. Do we know who Watson and Crick is? Who they were?
Well, my video just went out, so I'm looking to see why.
Oh, shoot.
Now they're coming back. Now I can see everybody.
Okay. So who's somebody in biology? How about Victoria, you're in biology. Who are Watson and who were they? Who are Watson and Crick? Do you remember? Anna, do you remember?
Something with like DNA replication, I think.
Yes, absolutely. So what I want you to do, this is a somewhat archaic paper that they wrote. We're just going to spend a couple minutes looking at it. This was published in 1953, so nearly 70 years old. And it was considered absolutely groundbreaking. So hold on. I put the link in Google Classroom, but I think you can see it on my screen as well. You don't have to be taking notes. Basically, I just want you to kind of get the gist of it, so it could be a skim read if you like. Let's at least read this first part. Do that silently, and then we'll talk in a minute. Okay, so I recognize that it's just a quick skim, but let's think about, so first of all, what is basically, what are they writing about in essence?
They're saying that, like, they're trying to show what this other scientist thought DNA looked like, and then they're using what they found to try to, like, disprove what he thought it looked like.
Okay, good. So they recognize that they're building off of other maps of what DNA looks like, and they're altering their model. Again, in 1953, what they could see was limited, and so they had to theorize a little bit using the science that they had available to them to start to understand how DNA actually worked. So one of the things that I wanted to point out, or I wanted to add, I wanted to point out to you is this idea of we wish to put forward this radically different structure for the salt of deoxyribose nucleic acid. This structure has two, so they put forth their own idea. This is their own new idea, and again, they won several awards, lots of accolades for this really groundbreaking discovery. But what I'm going to do right now is I'm going to show you a short video of another scientist. Do you know Rosalind Franklin? Just say yes if you've heard of her. Okay, so
lots of shakings of the heads.
Shakings of the heads. We don't know Rosalind Franklin, but even though we may not, we've heard of Watson and Crick. Most of us have at least heard of Watson and Crick. So let's take a look at this short video about Rosalind Franklin.
The discovery of the structure of DNA was one of the most important scientific achievements in the last century, in human history, in fact. The now famous double helix is almost synonymous with Watson and Crick, two of the scientists who won the Nobel Prize for figuring it out. But there's another name you may know too, Rosalind Franklin. You may have heard that her data supported Watson and Crick's brilliant idea, or that she was a plain-dressing, belligerent scientist, which is how Watson actually described her in The Double Helix. But thanks to Franklin's biographers, who investigated her life and interviewed many people close to her, we now know that that account is far from true, and her scientific contributions have been vastly underplayed. Let's hear the real story. Rosalind Elsie Franklin was born in London in 1920. She wanted to be a scientist ever since she was a teenager, which wasn't a common or easy career path for girls at that time. But she excelled at science anyway. She won a scholarship to Cambridge to study chemistry, where she earned her PhD. And she later conducted research on the structure of coal that led to better gas masks for the British during World War II. In 1951, she joined King's College to use X-ray techniques to study the structure of DNA, then one of the hottest topics in science. Franklin upgraded the X-ray lab and got to work, shining high-energy X-rays on tiny wet crystals of DNA. But the academic culture at the time wasn't very friendly to women, and Franklin was isolated from her colleagues. She clashed with Maurice Wilkins, a lab mate who assumed Franklin had been hired as his assistant. But Franklin kept working, and in 1952, she obtained Photo 51, the most famous X-ray image of DNA. Just getting the image took 100 hours. The calculations necessary to analyze it would take a year. Meanwhile, the American biologist James Watson and the British physicist Francis Crick were also working on finding DNA's structure. Without Franklin's knowledge, Wilkins took Photo 51 and showed it to Watson and Crick. Instead of calculating the exact position of every atom, They did a quick analysis of Franklin's data and used that to build a few potential structures. Eventually, they arrived at the right one. DNA is made of two helicoidal strands, one opposite the other, with bases at the center like rungs of a ladder. Watson and Crick published their model in April 1953. Meanwhile, Franklin had finished her calculations, come to the same conclusion, and submitted her own manuscript. The journal published the manuscripts together, but put Franklin's last, making it look like her experiments just confirmed Watson and Crick's breakthrough, instead of inspiring it. But Franklin had already stopped working on DNA and died of cancer in 1958, never knowing that Watson and Crick had seen her photographs. Watson, Crick, and Wilkins won the Nobel Prize in 1962 for their work on DNA. It's often said that Franklin would have been recognized by a Nobel Prize if only they could be awarded posthumously. And in fact, it's possible she could have won twice. Her work on the structure of viruses led to a Nobel for a colleague in 1982. It's time to tell the story of a brave woman who fought sexism in science and whose work revolutionized medicine, biology, and agriculture. It's time to honor Rosalind L.C. Franklin, the unsung mother of the double helix.
Oh, no. Can't read it.
Oh, you can't read it?
No, you can't read mine. Mine's flipped.
Oh, wait.
No, you can see it just fine.
Let me see. Liberate. Yes, 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 yes. Who else would like to opine about poor Rosalind? How do we connect this to our thinking about ways that we know about science? Did we lose somebody? Oh, no.
No.
Okay, good.
The only thing that I have to add to this is listening to this, it made me think of another section of the podcast, which was I think the last one, where he was talking about that there was 4 different things that can trigger a scientific breakthrough, and one of them was quote, the collision of radically diverse disciplines. And in the case of DNA, it was the X-ray crystallography, Mendelian genetics, biochemistry, and molecular biology. And so when it comes to finding or having these scientific breakthroughs or new ideas, it involves the cooperation of all kinds of different studies.
Thank you. Yes. Anyone else want to add to that? How about if we take a look at these questions for a moment, and I'll let you just look at them first, and then we'll discuss for a moment. You might want to jot some notes in your notebook as you think about these questions. So this notion that their opening sentence, this structure has novel features which have considerable biological importance. Does that feel ironic or small in comparison to what we now know of how our understanding of DNA has affected science? What do you think about that? Were they just being humble? Mr. Chisnell can see your faces, so he's going to call him one of you.
I look at people who are turning this over, but they're not sure. If I can offer it as a contrasted question, would you feel it was different if the first sentence of that article had said something like, "We've found the most amazing thing that's going to alter all of humanity and medicine forever." Exclamation mark 3 times, because they're in middle school. How would your thought about them change if they wrote it that way? Or would you care?
Would you speculate that they fully understood the hugeness of their discovery or their borrowing of others' discoveries? You don't want to offer an opinion on that? Okay. Fine. How about this? Did you understand all or most of Watson Crick's paper?
Or the parts that you read?
Yeah, you just skimmed it. But would you think that like it's a Reader's Digest kind of version of science, or is it for a different audience? Is it for everyday people or for people who are somewhat knowledgeable of the sciences?
I think that just based on what I read, that the majority of it would be it's a scientific journal, so it'd be going towards the scientific community. It's telling them what they found. It's not supposed to be, for the daily average person, especially during that time where you didn't have daily average people reading, these extensive scientific discoveries like that.
Right. So I'm going to skip right to how about we talk about this? If Watson and Crick relied on Rosalind Franklin's Photo 51, did they do science? Their paper is, what does it show? Did they do the science, or are they just thieves, or could they still be considered scientists?
Well, I think that goes into, like the last question was, the relationship between experimentalists and theorists. So the experimentalists would be someone like Rosalind, who did all of the work and did all the findings, but then Watson and Crick took all that work, put it together, and developed this one big theory.
So they're not just plagiarists. They're not just people who stole an idea. They still built off of other science. Am I paraphrasing you correctly, Tyler?
Yes.
Anyone else want to add to that? All right. So again, I would probably force you to talk about this longer, but because the time is short, I'm going to kind of rush us through. Here's some pictures. Here you see the people who are winning the award, and this Rosalind Franklin is basically in obscurity, but now you are knowers of this, and you can tell the tale of her impact on the study of DNA. So what I'd like you to do now, I'm going to actually just show you Nature website. So Nature magazine was where this famous paper was published. As Tyler mentioned, it's really for scientists. But let me just show you their digital magazine as it is today. And I'm going to find their, excuse me 1 second. Sorry, I'm looking. I've lost it. The
What were you-
about section. I'm looking for the about section. And maybe it was in here. About the journal. So I just wanted to
There we go.
show you this. So how about Victoria? Would you read the aims and scope?
Nature is a weekly international journal publishing the finest peer-reviewed research in all fields of science and technology on the basis of its originality, importance, interdisciplinary interest, timeliness, accessibility, elegance, and surprising conclusions. Nature also provides rapid, authoritative, insightful, and arresting news and interpretation of topical and coming trends affecting science, scientists, and the wider public.
Lovely. Anna, would you read the mission statement?
First to serve scientists through prompt publication of significant advances in any branch of science, and to provide a forum for the reporting and discussion of news and issues concerning science. Second, to ensure that the results of science are rapidly disseminated to the public throughout the world in a fashion that conveys their significance for knowledge, culture, and daily life. Nature's original mission statement was published for the first time on November 11th, 1869.
Yeah, so 150 years ago, right? This is an old, long-standing place where scientists can share their conclusions and, as we've seen, build off of other ideas. So are you guys on the website? Did you go to it, or are you just following mine?
I'm following you.
Okay. I'm trying, we're running out of time, but what I would love for you to do is sort of explore the Nature website, just the kinds of science that is there currently. As you can imagine, this topic is going to be prevalent in editions that are recent. And one thing that's sort of fun, just I'll want you to notice, and maybe I'll even ask you to put it on Google Classroom just for fun. I grabbed some of the really jargony, difficult, technical, and obscure sentences from some different editions of Nature. And I don't know about you, but it doesn't look like the English language to me. So there's some pretty heady, very specific kinds of science that you could find in this magazine that originally published Watson and Crick. So I'd like to go back to this before we leave. And by the way, I sort of as homework, I would like you to take a look at the ToK framework. Mr. Chisnell and I are going to work out how exactly we're going to sum up our natural science conversations, but one element of it will be for you to take a look at the framework. But looking at the ways of knowing, I would like to know how many of you, and Mr. Chisnell will narrate, how many of you would change your vote? Which two ways of knowing seem to rise to the top in terms of exploration of natural sciences? Do we have any people who would change their way of knowing?
Currently, I see no one saying they would change their vote.
Okay, could I at least have somebody explain why you're sticking to your guns and why you continue to feel that these two ways of knowing stand? And again, there's no right answer with this, but I just would like to hear your thinking on why do you hold fast and hard with the original ways of knowing, that you chose at the beginning. So Sarah, you want to start us? Tell us which two you picked and why you still stick with them.
I did reason and intuition, and I believe that like Bill Good is that like scientists first like have a hypothesis and that's like their intuition, and they have to believe in that in order to like try to experiment and go further with that idea. And then once they find like go through the steps and like figure out like examples of how it is, they have to reason through and try to figure out like a theory about to prove like what they found out from their experiments.
Thank you. How about Anna? Tell us which two you still feel are the prevalent ways of knowing in natural sciences.
I chose reason and memory. I guess I chose reason because like it's kind of what like experimenting is. Like you have to figure out like if your hypothesis was correct, or like you have to figure out the best way to like figure that out, I guess, which is what I would think to be reason. And you kind of have to have memory too to like figure out what could be like what has already been proven and how you could go to like not change that, but like think about it in a different way, I guess. I'm not sure, but
Be confident, Anna.
I know.
I like your ideas.
Anna, can I ask, when you talk about memory, do you mean the scientist's personal memory, or do you mean like a collective memory of all scientists?
I would say like a collective memory.
Okay. So it's kind of a shared memory or shared background or history of science, which propels the rest of it.
Yeah.
Thank you. Who's next?
Victoria, maybe?
Sounds good.
So I had gone with reason and faith, and just with reasoning, it's kind of the basis through experiments and figuring out what your hypothesis is, testing it, what the conclusion is, was it right, was it wrong, what went wrong. Faith, just believing in what you do, why you're doing it, other people who believe the same thing as you do, so on. Nothing else from our conversation or just thinking it over more made me feel like I should switch it at all.
Victoria, I wonder, before you started ToK, would you have considered reason and faith to be at odds with each other? Do you think that they are generally complementary ways of knowing, or does that seem perfectly logical to you that they can work hand in hand in the way that you described?
It depends on the context they're in. I guess most of the time when you think faith, you think religion, and usually, or until recently, I mean still recently, but faith and science is always, or religion and science is always kind of conflicted, but I don't know.
I can offer a thought or two or a question or two on that as we talk about faith. I've heard faith used in this last hour, maybe with three slightly different definitions. And I would challenge us to think a little bit about our definition of faith as we apply it to science. One definition of faith that is held by many is that faith inherently is irrational, is inherently without evidence or proof, and those are defining criteria for it. I don't know that that's a definition we all share, but it's a big one that's out there. And if that's the case, how does that play, as Victoria is wrestling with this question of reason? So just to think about and turn over about what our understanding of faith is and how broad our definition will get. And we haven't heard finally from Tyler on this issue.
All right, so the two that I had originally picked were imagination and faith. So when I think of science, and you don't really have new big ideas without imagination. You don't progress in science without, that big idea that pops into somebody's head as they're sitting alone in their study. So I think that without imagination as one of the core concepts of science, we don't progress, we don't get those new ideas. And then for faith, I know that now we're wrestling with the definition of faith, but when I think of it, it's, if you don't trust in science, you don't believe in science or the theories that come from science, then that defeats the knowledge that we have gained from it. I don't know if I'm wording it correctly as I'm thinking of it, but just if without faith in the knowledge, then what is knowledge?
Say that again, that last sentence.
Without faith in knowledge, what is knowledge?
Okay.
That's interesting.
Well, as always, we open up more questions than we answer, and I think that's really the point of the whole class, isn't it? Mr. Chisnell and I have some planning to do as far as how we're going to bring this to a close, but I would love for you to play around on the nature site. It is really interesting. I mean, you really honestly will believe that it's written in another language and some of the articles. So I'd like you to, a prize will be awarded for the person who gets the most obscure, the most unrecognizable to an English speaker. Whoever finds that, you win a prize. And then I also would like you, I saw a political cartoon that, oops. Sorry. And I know we have to get off, but I just wanted to leave you with the political cartoon. And I would like for us to collect some political cartoons that are dealing with science. And maybe that will also influence the way we are thinking about natural science as an area of knowing. And so this is obviously timely. And I would like you to search and see if you're finding any political cartoons. And they don't have to be from, the last month, but although there certainly are some available to you, but see if you can't find some cartoons that wrestle with ideas of science. So those are my two sort of challenges for over the weekend. And other than that, Monday we'll give you some direction about what we're going to do Thursday. I do think we will be looking at some kind of way to sum this up, and so we'll give you more directions on that. Any other questions before I leave you?
Okay.
All right. Thanks for wrestling with these ideas, guys. Thank you.
See y'all.